Welcome everyone. In today's lecture, we are going to discuss one-dimensional heat conduction, a critical aspect of heat transfer in engineering. Conduction is the process by which heat moves. Conduction is the process by which heat moves through a solid material due to temperature difference, and it is driven by molecular interactions. In one-dimensional conduction, we simplify the analysis by assuming the heat flows in a single direction, making it easier to model and solve the practical problems. This concept is foundational for designing the systems like building insulations, electronic cooling, and industrial heat exchangers. Today, we will explore the principles governing one-dimensional conduction, starting with the Fourier's law, which quantifies heat flow. We will also cover the assumption that simplify our calculation, the heat equation, and practical applications like heat transfer in walls or pipes. By the end of this lecture, you will understand how to analyze conduction in simple geometries and apply these principles to real-world engineering challenges. Whether you are designing a thermally efficient building or ensuring an engine doesn't overheat, one-dimensional conduction is important concept for this. So let's look into the fundamentals of conductions and see how it shapes the systems around us. Let's start with the basic of conductions. Conduction is the transfer of heat through a solid material caused by molecular interaction without any movement of the material itself. It occurs when a temperature gradient exists, meaning one part of the material is hotter than another. For example, if you heat one end of a metal rod, the heat travels to the cooler end through vibrating molecules. This process is described by Fourier's law, which we will explore in the next lecture. The material thermal conductivity, denoted by K, determine how easily heat flows. Metals like copper have high conductivity, while insulators like wood have low conductivity. The cross-sectional area A also plays a role, as larger area allows more heat to pass. Conduction is critical in applications like designing heat sinks or insulating homes. In one-dimensional conduction, we focus on heat flow in a single direction, simplifying the complex system for analysis. This approach is widely used in engineering to predict heat transfer in walls, pipes, or electronic components. Understanding conduction helps us to optimize energy efficiency and system performance. So let's move to the Fourier law to see how we quantify this process. Now we will see into Fourier's law. It is important in conduction analysis. The Fourier law states that the heat flux Q is proportional to the temperature gradient dt by dx and the material's thermal conductivity K. Mathematically, it is expressed as Q is equal to minus K multiplied by dt by dx. Here Q is the heat flux in watts per square meter. K is the thermal conductivity in watts per meter Kelvin, and dt by dx is the temperature change over the distance. The negative sign indicates that heat flows from hot to cold region. For example, in metal plate with one side at 100 degrees centigrade and the other at 50 degrees centigrade, heat flows towards cooler side and the rate depends on the material's conductivity and the temperature gradient. Fourier's law allows engineers to calculate how much heat is transferred through a material, which is essential for designing systems like thermal insulation or heat exchangers. By understanding this law, we can predict heat flow in solids and select appropriate materials for specific applications. Next, we will discuss the assumption that make one-dimensional conduction analysis manageable. So we are going to see the next important concept. Okay. The assumptions for one-dimensional conductions. To analyze one-dimensional conduction, we rely on several key assumptions to simplify the problem. The first, we assume heat transfer occurs in only one direction, such as along the length of a rod or through a wall. This eliminates complications from heat flowing in multiple directions. Second, we assume steady state conditions, meaning the temperature distribution doesn't change over time. This is typical in systems that have reached equilibrium, like a wall with constant temperature on either side. Third, we assume the material's thermal conductivity is constant, independent of temperature, which is reasonable for small temperature ranges. Finally, we assume no internal heat generation, so there are no sources like chemical energy or chemical reactions or electrical currents producing heat within the material. These assumptions allow us use straightforward mathematical models like Fourier's law to predict heat flow. They are applicable in scenarios like heat transfer through building walls or cooling electronic components. By simplifying the problem, we can focus on the core physics of conductions and apply these principles to practical engineering designs. So let's explore the heat equation in the next slide. The one-dimensional heat equation governs how temperature changes in a material during conduction. In Cartesian coordinates, the general form is given by partial differentials of d2t by dx square is equal to 1 upon alpha into dt by dt in partial forms. So here the T is the temperature, X is the position, and small t is time, and alpha is the thermal diffusivity. This equation accounts for transient, that is time-dependent heat transfer. However, in steady-state condition, where the temperature don't change with time, the equation simplifies to ordinary differential equation, which is given by d2t by dx square is equal to 0. This means the temperature profile is linear and the second derivative of temperature with respect to position is 0. For example, in a wall with one side at a temperature T1 and other side at a temperature T2, the temperature varies linearly between them. This equation applies to both Cartesian systems like flat walls and cylindrical systems like pipes, though the changes or the form changes here are slightly for radial coordinates. Solving this equation helps engineer to determine temperature distribution and heat flow in materials. It's a powerful tool for designing systems where conduction dominates, such as insulated walls or heat sinks. Next, we will apply these concepts to heat transfer through a plane wall. We will apply our knowledge to heat transfer through a plane wall, a common scenario of one-dimensional conduction. For a wall with a cross-sectional area A, thickness L, and thermal conductivity K, the heat transfer rate Q is given by Q is equal to K multiplied by A multiplied by dt or delta T and whole divided by L, where delta T is the temperature difference across the wall. This equation comes from integrating Fourier law over the wall thickness, assuming steady state condition. For example, if a wall separates a warm room at 25 degrees centigrade from a cold outside at 0 degrees centigrade, heat flows through the wall proportional to the temperature difference and the wall's conductivity and area, but inversely proportional to its thickness. Thicker walls or materials with lower conductivity, like insulators, reduce heat loss. This formula is widely used in building designs to calculate heat loss or gain, which helps the engineers to select appropriate or proper material and wall thickness for energy efficiency. It's also relevant in application like furnace walls or electronic enclosures. Understanding heat transfer to the plane walls is a practical application of conduction principle. Next, we will introduce the concept of thermal resistance to simplify these calculations. Thermal resistance is a powerful concept that simplifies the conduction analysis. It is analogous to electrical resistance in circuits. For a plane wall, the thermal resistance R is defined as R is equal to L divided by K multiplied by A, where L is the wall thickness, K is thermal conductivity, and A is the cross-sectional area. The heat transfer rate is then given by Q is equal to delta T by R, where delta T is the temperature difference across the wall, and this is similar to the Ohm's law, where current equals the voltage divided by resistance. High thermal resistance caused by the thick wall or low conductivity material reduces heat flow, which is why insulation is effective. For example, adding fiberglass insulation to a wall increases its thermal resistance, keeping building warmer in winter. Thermal resistance is a key tool in engineering, allowing us to quickly calculate heat transfer in complex systems like multi-layer walls or composite materials. By treating conduction as a resistance problem, we can analyze and optimize systems efficiently. Let's move on to conduction in cylindrical geometries like pipes, where thermal resistance takes a different form. Now, let's explore heat conduction in cylindrical systems such as pipes or insulated cables. For radial heat conduction in a long cylindrical pipe with inner temperature T1 and outer temperature T2, the heat transfer rate is Q is equal to 2 pi Lk multiplied by T1 minus T2 divided by natural log of R2 divided by R1, where K is thermal conductivity, L is the pipe length, and R R2 and R1 are the outer and inner radii. The term natural log of R2 divided by R1 accounts for the radial geometry as the heat flow outwards or inwards through concentric layers. The thermal resistance for a cylindrical layer is given by R cylindrical is equal to natural log of R2 divided by R1 divided by 2 pi Lk. This formula is crucial for analyzing heat loss in pipes carrying hot fluids or designing insulation for pipelines. For example, in a steam pipe, thick insulation with the low conductivity increases resistance and reduces the heat loss. This analysis is also used in electrical cables or nuclear reactors where radial heat flow is significant. Understanding cylindrical conductions helps engineers to optimize thermal performance in industrial systems. Next, we will look at practical applications of one-dimensional heat conduction. Applications of one-dimensional heat conductions. One-dimensional heat conduction has a wide range of applications in engineering and daily life. For it's critical in analyzing the heat transfer through walls and roofs of buildings. By calculating heat loss, engineers design insulation to reduce energy cost. Second, thermal insulation in pipes like those in HVAC or oil pipelines relies on conduction analysis to minimize heat loss or gain, ensuring efficient operation. Third, the cooling electronic components such as computer chips, which involves managing conduction through heat sinks to prevent overheating. Finally, the heat dissipation in engine blocks like those in cars depend on conduction to transfer heat from hot combustion zones to cooler systems. These applications show how one-dimensional heat conduction principles are applied to improve energy efficiency, safety, and performance. Whether it's keeping home warm, protecting electronics, or optimizing industrial process, conduction analysis is a vital tool. Let's conclude with a summary of what we have learned about one-dimensional conduction. To wrap up, in today's session, we have seen one-dimensional conduction, which is a fundamental concept in heat transfer analysis, essential for engineering design analysis. The Fourier's law, which is given by Q is equal to minus K dt by dx, governs how heat flows through the solids due to a temperature gradient. The thermal resistance concept R, which is given by R is equal to L by Ka for plane wall, or R cylinder is equal to Ln of R2 by R1 divided by 2 pi Lk for cylinders, simplifies our calculations, making it easier to predict and optimize heat transfer. We have explored the assumptions that enables one-dimensional analysis, the heat equation for steady state and transient conditions, and practical applications like building insulation, pipe designs, and electronic cooling. These principles allow engineers to create energy-efficient automotive and electronics systems in which one-dimensional conduction is a critical tool for innovations. I hope this lecture has deepened your understanding of conductions and its real-world impact. For next time, consider how these concepts apply to a system you encounter, like a radiator or a laptop. Thank you, and let's keep exploring heat transfer.